Parabola's definition is the equidistance from the focus, which is at the pole at the moment, to the curve, and from the curve to the directrix, correct? So it's a sideways, but you've seen this picture before, right? Okay, but in polar equation, this is what we call R, right? And R is being measured right here. And then I'm calling this thing capital D. This thing is capital D, and which is exactly equal, right? And then you were taught somewhere that eccentricity of parabola is exactly 1A. Because the eccentricity as it was defined in pre-calculus was C over A. So in case you have an ellipse, C is smaller than A, so you have eccentricity less than 1. And hyperbola, C is greater than A, so you have eccentricity more than 1, right? But when it's equal, I was like, and then Z circle, right? Those are the things. And then I have located this thing, directrix, exactly at 2 units. That's what this thing tells you. So when you say lowercase d, that's the distance from here to here. And when we have uppercase d, in this case, is that distance right there. So far, so good with me? Now, I'm going to change the eccentricity and see what happens. If I reduce it, I'm going to move it a little bit this way so we can see it better. About there. If I keep reducing it, then, this thing becomes an ellipse. And as you can see, this distance, which is measured right there, versus this distance, which is measured right there, and the ratio of the two, this over this is what we really the definition of eccentricity. How about that? So, and as you can see, one distance is greater than others, so it'll eventually come back around. But this has to be shorter than this one. And there was like one of the, what was it, the math competition had a question like this. If you have set up all these things with that ratio, what does it give you? Where is an ellipse? Okay, math team people, you remember seeing these things? Guess not. Okay. And then if I reduce the eccentricity down, see, as it gets closer to 0, it becomes more and more circular. Remember that story about Newton and Halley? All of the planet motion, they thought it was a circle, but it turns out to be slight ellipse like this, eccentricity very close. So we say, take a limit, and when eccentricity is 0, that's a circle, but it's a point circle. You know what I'm saying? Okay, so, and then this is like most planets, and then something like Pluto, maybe it's about that, and then Comet has eccentricity like this. You know what I'm saying? So then, wow, can you imagine what this graph will look like if I make the eccentricity more than 1? Watch this. I didn't realize this until I made this and saw it, but whoa, it comes back from the other side and becomes a hyperbola. And as you can see, this distance right here is more than that distance. This got me thinking, and this is just my pure speculation. You guys heard about the curved space and time? Curved space-time? Just like on the surface of the Earth, if you keep traveling in the same direction forever, then eventually you come back to exactly the starting point. So is a hyperbola really a gigantic, ellipse that wraps around the universe like a tennis ball? Okay, purely my speculation. Okay, so now we are going to derive this. So I'm gonna make it nice size ellipse. It doesn't matter what it is, but I'm gonna make it look like an ellipse at the moment. Okay, and I'm going to copy this. That didn't work. Okay, I'm gonna try copying it again. This computer is just, let me try copying that again. Okay. I'm gonna need about that much. Okay, now this is Conics in polar coordinate. Okay. Let's start right here. Zoom in so it can work. So let's define a few things here. Remember I said D. When I said D, it was from here to here. This was D. Remember that? And then this is R of data, of course, our function. This is our R vector, right? Okay, and then of course this will be theta. And then this was capital D, but I want to figure out the expression for capital D. Okay, here's a right triangle. So that capital D, which is that much, would be D minus R cosine theta, which is this thingy right here. You agree with me? Okay, now that on the side. So our eccentricity by definition was R over capital D, right? Distance from the curve to the focus, and this from that point to the directrix, right? And then directrix is exactly lowercase d units away from the pole. If you are confused about this, let me know, and I need to keep track of time. 10:45. Okay, so I have about 20 minutes. I think I can do it. But that denominator d now is equal to lowercase d minus r cosine theta. You with me? Okay. Now I'm going to multiply the denominator to the other side. So we have ed is equal to, or ed minus er cosine theta is equal to r. So far so good? Okay, then ed is equal to the other side, r common factor, so 1 minus e cosine theta, 1 plus e cosine theta to the other side. Too much algebra? Okay, so here comes the equation. R, which is a function of theta, by the way, let me remind you, is ed divided by that thing. Oh, this is it. That's remarkably simple now, isn't it? This is the equation of the polar coordinate conics. Which one? It's all of it. This is ellipse, parabola, and hyperbola, as I showed you. It all depends on the value of E, eccentricity. Okay. Now we have to still justify and relate that with our Cartesian coordinate, eh? Okay, so let's go back here. Let's go back to this line. So I have this ed minus e to the r cosine theta is equal to r here, okay? Now, can we convert it into Cartesian coordinate? Yeah, let's do that. So what is r cosine theta here? That's x, isn't it? So we have ed minus x, or ex, and that is equal to r. Guess what I'm about to do? We square both sides, so we have d squared minus 2 e squared dx plus e squared x squared. Too much algebra? And then this, of course, r squared is x squared plus y squared, eh? Say yes. Okay, I'm gonna have e squared d squared is equal to, put it to the other side, and let's common factor it. So I have, do you see this x1 minus e squared common factor, x squared, between this thingy and that thingy. And then I have plus 2e squared d. Oh, d. This is d times x. That also looks like dx. The calculus, yeah, lowercase d in calculus is very dangerous, but that's not our infinitesimal dx. No, 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 no. Okay. And then we have plus y squared. With me so far? Okay. Then, hate to tell you this, but we have to complete the square. Have you completed a square of something this magnitude before? Let's have e squared, d squared, space here, and then we have to divide both sides by 1 minus e squared, right? Oh, I jumped the gun prematurely. D squared over 1 minus e squared is equal to x squared plus 2e squared d over 1 minus e squared x out here to make it a little less. And then I'm going to leave a space here, space plus y squared 1 over 1 minus e squared y squared. How about that? You with me so far? Say yes. Okay, now I'm going to add same thing on those sides, but this is my technique. That same thing that I'm going to add is kind of hard to see. So let's just go to the next level. Is it always half of that thingy? So we have e squared d over 1 minus e squared quantity squared a. And then that tells us what we are going to put here, which is e to the fourth d squared over 1 minus e squared quantity squared a. Now I'm going to add that. I was right. I should have left a space here, but hey, I can do this. So I will add that same thing on both sides. You with me? Okay, so what we have is, now I'm going to combine these two expressions on the left-hand side. So we have 1 minus e squared, quantity squared, 1 minus, and then multiply it here, right? So I have 1, so I have e squared, d squared, minus e to the fourth d squared plus e to the fourth. Oh, they cancel. Isn't that nice? And then on this side, I have x plus e squared d over 1 minus e squared quantity squared. And of course, I forgot to write 1 over 1 minus e squared y squared here. Which I'm gonna, I of course forgot x squared as well, right? No, x is in there. So I have 1 over 1 minus e squared y squared. You with me? How are we doing so far? Too much algebra? Now divide both sides by this thingy. So I'm going to have x plus e squared d over 1 minus e squared quantity squared over e squared d squared over 1 minus e squared quantity squared plus, now this side is a little tricky, but I think you can do this over e squared d squared and just 1 minus e squared a. Right. Too much algebra is equal to 1. Now, let me know if this is too much algebra. Now is the time. Okay, well, that now took a nice shape, right? Let's just figure out. This must be an A, right? This must be an B. Right? Okay, but this just looks like ellipse at the moment, right? How do you justify this is everything? Okay, and okay, let's do this. So it all depends on these three cases. Case 1, if E is less than 1, if e is less than 1, you notice that this a, this term a, oh, this is a squared, and this is b squared, right? Well, then a squared is always positive, right? So what we have is a squared is positive and b squared is positive. Well, that gives us an ellipse now, doesn't it? You get it? Okay. Case 2. E is greater than 1. A squared is still positive. I hope you see that, because everything is squared. But b squared, let's see, this numerator is positive, but this denominator is negative now, isn't it? So b squared is really negative. And that'll give us, of course, hyperbola, right? Huh, that's amazing. Well, case 3. E is equal to 1. If e is equal to 1, we cannot even do this because the denominator is equal to 1. So we have to back up. Let's back up in our equation and set e equal to 1. We have to go all the way here, right? So I'm going to pick it up from there. We should have probably took care of this first, but they do it now. So e is equal to 1, then what we have is this. This equation simplified to d squared minus 2dx plus x squared is equal to x squared plus y squared. You see that? These two cancel. So you have d squared minus 2dx is equal to y squared. That sure looks like a parabola opening this way, right? Amazing, amazing, huh? Last thing to verify, because eccentricity, this according to formal definition from our geometry is this, but eccentricity from pre-calculus book is c over a. So is that really the case? Well, we'll see. So a and a b, I have a and a b here, right? So I'll take a square root of these things and which is a, this is a and a b square. I'll take what I have in the notes is not correct. Okay, I'll just take a c over a was, this is correct. We have to calculate c squared, then take c over a, right? So remember in this c squared, let's do it this way. Remember a squared was equal to b squared plus c squared. Now this includes everything because this b squared could be negative as I shown you earlier. So this is our thing, and that tells us that c squared is equal to a squared minus b squared, right? Okay, and let's figure out what that was. A squared from up here is this, and b squared from his. Okay, try to remember that. I'm going to write it down. So a squared is e squared d squared over 1 minus e squared quantity squared minus b squared is e squared d squared over 1 minus e squared and no parenthesis, like that. Okay, in order to multiply this, of course, we have to do this, right? But in order to subtract. Then we have a common denominator. And then numerator cancels, see, this term cancels this term. So we have negative, negative, positive. So we have e to the 4th d squared. So far, so good. Okay, now, then I'm going to take c over a. And let's see if we get eccentricity back. So c is square root of what we just calculated, which is this. Okay, no parentheses because we took a square root of this. And then over A, and A is this first term here, flip it over and multiply. I think I didn't take a square root, so like that. Good? Very good? The square root of that thing is A. Now let's cancel a bunch of stuff. E, as you were taught before. Amazing, isn't it? So this thing can be converted into Cartesian form. Any questions?
Why don't we need plus or minus when you find the square root of C, since everything's like the second power or the fourth power?
Okay, let's go back to yesterday's stuff on, yeah, generally you want to put plus or minus, but the way we defined our thing here, it's just a physical distance, A, because there's the other side too, A, negative A, so it's the same thing. So for our purpose in conics, A, B, C are positive numbers, right? So we can figure out C and negative C as a coordinate. How about that? B and negative B, they are all there really, okay? So it's just the physical distance ratio is the what eccentricity is. So that's why, because you can see why the pre-calc books and teachers didn't want to do this, right? So they just say, okay, eccentricity is as if it's a definition C over A, but it wasn't really not a definition, this was.